So, hello everyone. My name is Paloma Ortiz. I'm from Leitat Technological Center, and I participated in the Nefertiti project within the pervaporation unit for ethanol purification. We are going to share with all of you a chapter entitled Next Generation Pervaporation Membranes for Ethanol Purification. So this is the overview of the presentation. First of all, we are going to do a general introduction of the application and how it has been implemented at industrial scale. And then we will talk a little bit more about the membrane, that is the core of the separation, and how we want to upgrade it and how it is applied in the Nefertiti project. As general introduction, we need to talk about organic solvents. Organic solvents such as ethanol are key in several applications, such as petrochemical industry, food industry, pharmaceutical. But we also need to think about how we want to recycle these solvents that we are using and how we want to remove them, for example, from water streams. For that, it's key to have efficient separation technologies, such as the ones that you can see here: distillation, quite conventional and mature technology, absorption, liquid-liquid extraction, and membranes. Each of them have their advantages and disadvantages, but the one that we are focusing here are membranes because they don't have the limitation of the vapor-liquid equilibrium. They also can operate at lower temperatures, and they don't require a regeneration step, that are one of the main advantages over the other technologies available. One thing that it needs to be improved, especially for more emerging applications, is the membrane stability and selectivity towards a specific component. And that's the target that we are focusing here with the development of new membranes. More specifically, the use of membranes in pervaporation and vapor permeation. The objective here is to combine the evaporation that we could find, for example, in distillation, with the permeation of the species through the membrane. The membrane itself is a selective barrier that will separate the species depending on the size, the affinity of these species to the membrane, and also their diffusion. This mechanism is called, as you can see here, the solution diffusion mechanism, that will consist in several steps: the absorption of the species in the membrane, the diffusion, and then the desorption. In here, we will have a chemical potential gradient that can be translated in parcel pressure, because typically we will have vacuum in the permeate side. Then, depending if the feed is in liquid or vapor, we will have either pervaporation or vapor permeation. But the separation is quite similar in both. Now, pervaporation has already implemented at industrial scale. It started in the early 80s with the development and industrial scale of membranes, hydrophilic membranes, for the industrial application in the dehydration of ethanol. Nowadays, we can find a lot of research work in this application and in the membranes. We can find a lot of manufactured companies of membranes and also pervaporation installations. The applications that we can find implemented are mostly focused on the solvent dehydration and the organic recovery, especially integrated with distillation in order to optimize the energy requirements. But more and more, they are more interested in applying this technology, for example, with reactors. Then we have what is called membrane reactor. We combine two separated units, the reactor and the separation unit, in a single one. And you can combine this also with a catalyst in order to have catalytic membrane reactors. And also, there are other emerging applications in which pervaporation is of interest. For example, in here, I show you desalination. Now, the membranes, the core of the application. Depending on the type of separation that we are looking at, we need to consider different types of membranes. For example, if we are looking at the solvent dehydration, we want to promote the transport of water over the organic species. So in here, we will look at hydrophilic membranes. If we want to recover the organic species, we will look at hydrophobic membranes. And also, if you want to separate two organic species, depending on the polarity, you can find that it can be applied either hydrophilic or hydrophobic. Now, when we are looking at the membrane, we also need to look at the material of the membrane. We can separate them in inorganic and polymeric, for example. Each of them, they are already implemented at the industrial level, and they have their own advantages and disadvantages. Now, next generation membranes, one approach to improve membranes is to combine these two types in what is called mixed matrix membranes. In here, what we apply to do is to mix the filler, the inorganic material, into the polymeric matrix, typically just by blending both. Now, the key factor is to have a good compatibility of the polymer and the filler, and to have an adequate dispersion of the filler in the polymeric matrix. And that's why it's really important the type of filler that we are using. It can be separated in 4 categories, depending if we are looking at the dimension characteristic of the filler. If we look at the 0-dimensional fillers, we are talking about nanoparticles, small nanoparticles of a metal oxide. Then we have the 1-dimensional fillers, such as anything that is like a needle-like shaped nanomaterial, like nanotubes, nanorods, and one typical and quite used one is the use of carbon nanotubes. Then 2-dimensional fillers are nanosheets, in which we can find graphene and graphene oxide, and also 2-dimensional nanoporous fillers. And finally, the last type is the 3-dimensional filler, in which we will have nanoporous materials such as the well-known zeolites, or more new and emerging nanoporous materials such as metal organic frameworks, covalent organic frameworks, and so on. Now, in Nefertiti project, we applied to introduce and to develop efficient next generation membranes using this approach, in which we will try to improve conventional polymers by the incorporation of nanoparticles. This we integrated in the project after the production of the ethanol in the membrane separation unit. It will be developed by Leitat, and more specifically the Membrane Technologies and Functional Materials unit. Our approach is to, depending how much ethanol we will have in the last stream, we will modify for ethanol dehydration or for ethanol recovery from water. Each of them will require to use different polymers, hydrophilic and hydrophobic, but as a filler, we will use metal organic frameworks, mostly because they are crystalline nanoporous materials with appealing properties in terms of sorption capacity, and also because they have a hybrid nature. They are metal ions or classes connected by organic linkers. And that's what makes it to have better affinity and mixability with the polymers. So in here you can finally find some related literature in which we have based this chapter. And finally, I would like to thank you for your attention. Thank you very much.